So, Philippines problem. It may be a four, will be given a grid, 4 cross 4 grid or 8 cross 8 grid. And we have to place 4 fields here and 8 fields here, or n into n matrix. And n means we have to place n fields in a grid in such a way that no two queens are in such a way no two queens are attacking each other. So here, let's take this example. We have to place 4 queens in a 4 cross 4 grid in such a way that no two queens are in the attacking position. Right. Let's take an example of 4 cross 4 grid. Now I have to place 4 queens here. Right. This means 1, 2, 3, 4. For a queen, so for 2 queens are not attacking each other. Where they are not in same row, they could not be in same row or same column, or they should not be same diagonal. Then we can say that no two queens are attacking each other. Let's see. I have to select 4 positions for the keys. How many ways do we have? I can select them without any conditions. There are 64 ways. For the solution, I'll just select the column. I'll say that in each row, I'll place only 1 queen. So I'll place the first queen in this row, second here, third here, fourth here, and I'll select the column such a way that no two queens are attacking each other. So first, let me write a solution to the funds. What will be the solution to it? If my first queen is here, let me write it. I'll take this Q1 is here. Q1 is in first column, first row. Then Q2 can be, it can be in first. Q1 can be in here, here, or here, or here. So I'll select like this. It can be third and fourth. Now Q1 I get it here. Here I can keep. Now here I cannot keep Q1, right? Because I should not keep in the same column. It can be 2, 3, or 4. Right. Here it can be 3 or 4, the third thing. The last one will be only one position like this. So everywhere we have the same one, right? So how many solutions will I have? It will be 1 plus 4 the second level. And how many are there in third level? Third level, I have 3 to 4. Plus in the fourth level, I have 4 to 3 to 2. That is 1 plus 4 plus 12 plus is 12 to 24, which is the 5 plus permeability plus every time I have one more right. It is 2 into 2 into 2. It's 24. So what is this? 570 41 65. I got 65 weights. But here, all these cases are not possible because I cannot select Q2 here, which means Q2 in second position. This one is not valid at all because it is in the same diagonal. Right. Now, how can I say the number of ways? It is 1 plus sigma of equal to 0 to 3 product of 0 to 4 minus 0. For n cross n, it will be n minus 0. Right. This is the maximum number of ways. But now I'll draw a map. This is called state space tree. Now using backtracking, we will try to draw what are the several ways in which we can draw, in which we can keep the fields in such a way that no two pins are attacking each other. Right? My green one can be in first column or second column or third column or fourth column. Okay. Now I'll take this condition where my Q1 is here. Now my second queen can take. You cannot take first column, right? Because it will be on the same column. So, and row we need not check because we are keeping here on. Now, can it be in the second column? Here? No, because it is in the same diagonal, it cannot take this. We are cutting it off. Can it be in third column? Yes, it can be in third column. Now, if it is in third column, where can my Q3 can be? It cannot be in this column and this column. It cannot be here because it's the same diagonal. It cannot be here also because it is in the same diagonal. So it can be in second column and fourth column, but both are not possible. So we are backtracking. What if we keep the second one here? Is it possible? Yes, it is possible. Now where should I keep Q3? I cannot keep it here, but then I can keep it here. So Q3 will have second column and third column. Third column is not possible because of our bonding condition. What is our bonding condition? Our bonding computations are it shouldn't be in same column, same row, same column, or same diagonal. So I'm tracking it off. If Q3 is here, I have only one space left for Q4, that is here. But can I keep it here? It is the same diagonal, so I cannot keep it here. So Q3, the fourth queen in the third column is also not feasible. So all the cases where my queen is in the first column, I will not have a solution for n queen solution because all the cases we are not meeting the bonding conditions. We are not meeting the bonding conditions. Okay. Now let's see if we keep Q3, my first queen here. The second column. I'm keeping Q2 here. So my second queen can be in first column, second column, third column, or fourth column. Can it be in here? No, it is in the same diagonal. Can it be here? No, it is in the same diagonal. Can it be here? Yes. So this is not feasible. This is not feasible. This can be possible. So I'm writing Q2 here. Now where can I keep Q3? I have only two positions here and here. I cannot keep Q3 here because it's the same diagonal. But I can keep it here. I have two, 1 and third column, but this is not feasible. So I can keep it in one, Q3. Now I can keep Q4 here, right? Q4 can be at third column. So one of my solution is 2, 4, 1, 3. 2, 4, 1, 3. So in each column, I can have like this. What will be the other solution? One more solution will be the mirror image of it. And here I don't have any other solutions. Right. So I'm leaving it like that. Leave it. I got one solution here. Now what if I have my queen in third column? I cannot have here and here. I cannot only have here. So I keep Q2 here. In first column, my Q2 will be in first column. Now I have here and here. I cannot keep Q3 here because it is in the same column. I have only here Q3. So it will be fourth column. Now I have only one. I can keep it here. Q4 will be here. That is 3, 1, 4, 2. This is one solution. What if I keep my queen in the fourth column? If I keep my queen at fourth column, I can keep my second queen in first column or second column. So first column or second column. Let's take this condition where I get queen here. I cannot keep my queen here, so I keep queen here. That is third column. If I keep queen here, I cannot keep anywhere. So this is not a feasible one. So I keep it queen here. If I keep my queen here, I cannot keep my Q3 anywhere. So there is no solution here also. So for a 4x4 grid, we have two solutions. Those are this one and this one. We have 65 ways, but we didn't calculate all 65 ways, right? Whenever we see a non-feasible way, which is not meeting our bounding conditions, we stop there and we try to backtrack it. So it's 2413 and 3143. What is the condition I used? I took the condition that I'm only keeping all the columns in each row. I'll keep one queen, and I have to keep the queens in such a way that no two queens are in the same row, same column, or same value. These are my conditions. Now I'll join through my laptop and let's try to see how can we convert these bounding conditions into an algorithm. And with backtracking, whenever we find a non-feasible way, we have to stop it and we have to find the solution. Right? Let me join through my laptop. Okay. Now we just followed a simple rule that no two columns, no two queens are in the same column or same row or same diagonal. And each time when I'm increasing row, I'm doing this till my row will be equal to length of board. That is, the length of board is 4 initially. Till I place all the queens, that is, when I place all the 4 queens, my row will be 4. 4 will be equal to length of board. Then I'll return true. It will stop. That is my base condition. And I'm using recursion here for solve queens. And whenever I'm going to place a new uh, queen, I'm simply calling the queen is safe. I'm calling the is safe function where it is checking that I'll give the board, row and column. By the given board, it will check that whether I can keep the queen in the given column or not. If I can keep, it will return true. If any condition that is present here is true, it will return false. So it's not possible for a 3 cross 3 grid to contain 3 queens. Then it is giving a wrong solution, right? So I'll send you this code. Please try to solve it. And whenever we get a non-feasible answer like this, it should not print this, but instead it has to say that it is not possible for this n cross n grid. It is not possible to have an n queen solution. Okay. I have sent you the IPYNB file. Otherwise, I'll send you the PDF file also. Go through it. It is very simple. Okay. Now take 5 minutes a break. We will start the ninth lab also today now only after 5 minutes. Now the time is 6:40. We'll start at 6:45. Okay. Now let's say the ninth lab. It's developing the program and measuring the runtime. First, graph coloring the backtrack. It is graph color. Uh, it's graph color. Using back color. What is the question first of all? Let's try to understand. Graph coloring is nothing but we'll be given a graph and few colors. We have to color each vertex of the graph in such a way that no two adjacent or neighboring vertices have same color. That means if I have a graph like this, I have to color each vertex. I have four vertices here. I have to color each vertex in such a way that no two adjacent vertices have same color. If the first vertex has the color yellow, second and third should not have the color yellow. It can be any other color, but they should not be yellow. They can be red. They both can be red. They both can be same color because they are not neighboring. Right? They are not adjacent vertices. But if these two are red, this cannot be red. But this can be yellow. This can be green. This can be white. Any other thing. So this is the graph coloring problem. We have to color each vertex of a given graph in such a way that no two adjacent vertices have the same color. Okay. Let's take an example. And take 2, 3, 4, and 5. Right. And I have three colors: red, green, and blue. RGB. I am randomly selecting the first color as red. This is red, so this cannot be red. I'm selecting green here. If this is green, what can be, well, this can be red. So I'm selecting red. This can be green, so I'm selecting green because the disadvantage source are not having green. This cannot be red. This cannot be green because it is adjacent to the first node, red, which is red, so it cannot be red. It is also adjacent to the fourth node, which is green, so it cannot be green. It should be blue. So one solution is RGB. This is one solution. This is the only solution. So it can be green, red, blue also, right? Green, red, blue. Like that, we can have so many solutions. We can have a blue here, blue, green, red, blue, green, red. That is one solution. So like this, we can have so many solutions. Actually, even before graph coloring, we'll have two more problems, which are called M coloring, decision problem. The output of this problem is either true or false. When we give it a graph and set of colors, it will say that whether it is possible to color all the vertices in the given colors and form a graph coloring in such a way that no two adjacent matrices are possible or not. If it is possible, we'll get the output as true. If it is false, if it is not possible, we'll get the output as false. And there is one more problem, that is M coloring optimization problem. see, here I have 5 nodes. So if I have 5 colors or colors, or more than 5 colors, it is very simple, right? Each node I'll keep a different color. Then I'll have that is one solution. Red, blue, green, white, yellow. All the nodes will have different colors. So that node to adjacent vertices will have the same color. If I have all the unique colors, there is no possibility of having the same color for 2 adjacent vertices, right? So that's not the case here. This will give the minimum number of colors required. Minimum. Wherever it is minimum, this is the optimization problem. Minimum colors required, minimum number of colors required for the given graph to form a to make graph coloring in such a way that no 2 adjacent vertices are same color. Now let's take an example, a simple example. 1, 2, 3, 4. This is my graph. And I have 3 colors, R, G, B. 3 colors. So I'm starting from 1. This can take. Now again I'm drawing a tree, state space P. First I'll randomly draw. Okay, I'm not using the bounding condition here. First we'll draw the tree and see the number of ways. Then we will try to draw the tree in such a way it is following the bounding condition. The first vertex can take either red or green or blue. Alright. If it takes red, what should my second node can also take? Red, green, blue. This is the first, this is the second. My third can take red, green, blue. And my fourth also can take red, blue, and green. Like this, we have all possibilities, right? So what will be the number of ways for this? It is 1 here. 1 plus 3 plus 3 into 3 plus 3 plus 3 into 3 into 3. 3 into 3 into 3 plus for each 3 I have 3 and again I have 3. What is 3 into 3 into 3 into 3? What is that? 1 plus 3 plus 9 plus 27 plus 81. 90, 30, 120, 121. That is 121 ways. I have 121 ways. But what if we try to draw a state space P by following the bounding condition? We'll try to draw. Keep this picture in mind. This is our graph. Right? And I'm drawing state space P. Right? And first, vertex can take either red or green or blue. That could be anything. Now, a second vertex cannot take red because it is already red. So that condition is cancelled. But it can take blue. Right? If it takes blue, the third vertex can take red. Right? But it cannot take blue. Blue is cancelled. It can take green also. here. This is red. This is blue. My third vertex is red again. And my fourth vertex cannot take red, can take green. So this is one solution. RG, RG. What if it took R? Sorry, it is RB, RG, RB, RG, RBG, and it can take RB, and if this is green, this can take blue, right? It can take blue, but this cannot take red or green. So I'm canceling. It is RBGB. RBGB is one solution. So I got two solutions here. Now, this is for B. What if I select green here for the second one? Here it is green. Now my third node can be red, blue, or green. It cannot be green. This is green, so this cannot be green. This can be red or blue. If this is red, this can be blue or green, right? But not be red because it is adjacent to two reds. So it can be blue or it can be green, but it cannot be red. And cancelling it. So it is RG, RB, RGBG, RB, RB. Sorry, RG, RG. This is one solution. Like that, we will have two more solutions if you draw the same thing here. But here we are not trying all the 121 ways, right? We just cancelling out wherever it is not possible, and then few steps we are finding. But generally, what is the maximum steps in the worst case? That will be 3 power n. Then n is the number of vertices. Right. Now, actually, why is this problem created? Means in the initial days, when we have a map, and to distinguish between all the different parts of the map, consider this as a map. And I have different states present, right? So whenever I want to color this map, initially we have to send this paper into the printing machine, the coloring machine. We have to send this 4 times into the machine if we want to color 4 colors. So if we find the minimum number of colors that are required, we can simply send it only that many times. So if we draw a graph for this, it is simply all the connecting nodes. If you draw a graph for this, this is the graph. And for this graph, if you find the minimum number of colors required, you can set this into the printing machine that many times. Then it is fine. We are reducing the time of sending this paper into the coloring machine. But now we have we are advanced in technology. We have printers that can print all the colors at a time. In a single go, they'll print all the times. But if you know the process, or if you know the problem why we are creating like this, whenever you find something related to this, you can use the graph coloring method and you can solve it. Now let's try backtracking in programming and find how can we get to the solution using backtracking. Actually, if you see the previous step where n queens, when we solve the n queens, there also we draw this state space tree, right? And using the bonding conditions, in this state space tree, using the bonding conditions, we calculated the correct way to keep 4 queens in the given board in a 4 plus 4 grid. Similarly, here also we are using the state space tree, and we are backtracking them whenever it is not feasible. We are going to the previous node and changing its place. So our pen and paper approach is also same or similar to the previous question. Similarly, our program will also a little bit looking like the previous problem, the inference problem. I'll join through my laptop and let's try to code.
Okay, you can see my screen, right? And give me 2 minutes. I'll open my previous code also. Now you know the logic. And for the eighth lab, for the Queen's lab, we saw the pen and paper approach using backtracking by simply drawing a state space tree. And we tried to see whether it is safe to keep a queen in the particular row or column by using the by using if you can see my screen, this is the previous lab that we have did, and I'm using eSafe function. This is very important. These are the condition. What are the bounding conditions that we have when we are solving this question in pen and paper using pen and paper will be in eSafe method, because every time I have to check whether it is safe to keep my queens in that particular row and column or not, right? And what are the bounding conditions for the ninth lab? That is uh, graph coloring. No two vertices should be same color. How can we know that two vertices are neighbors? First of all, we'll be given a matrix, right? Adjacency matrix, because they are giving a graph. They'll be given a adjacency matrix where we can find whether we have a way from this vertex to that vertex. If we have that adjacency matrix, we know that whether we know whether we have a way from a particular vertex to another vertex. If we know that those two vertexes have a way between them, that means they are neighbors. That means they both cannot have same color. So this function, it will be similar to this. So I'll use it. Just the conditions and the parameters will change. That's all. In a graph, whether that vertex can be colored in such a way or not. So eSafe method will be the same. I mean, the functionality will be the same. Maybe the function will change, because here we are using a 2D matrix, the adjacency matrix. There, we have to color each vertex. So we'll store the vertexes color as, say, we'll represent them with numbers. That will be easy. If you want, you can name them. I'll leave it to you. But if you use numbers, it is very simple to color them, right? Okay. And what is Solquins doing? Solquins is not doing nothing but trying each and every approach and whenever it is having something, some bounding condition failed, it is returning false, and it is again starting the condition by increasing the row. So whenever I place a queen, it is increasing my variable row, and again it is starting to, it is recursively calling the solve kills, right? So here, let's try to do it. Let me name my, let me name, I'll do one thing. I'll write all of these in the class named graph, because we are, these are all graph properties itself, right? So if I write in the class graph, I can simply use it on any object which is of type graph. And I'll change this function afterwards. Now I'm commenting it, but I'm going to use it definitely because I have the bounding conditions here also for this problem also. I'll write graph coloring, which will take my graph. uh, it will take a color. I think I will need few more. Let I'll need few more, right? Let me start with the parameters first. Let's assume they'll give me a graph. Let's take the same graph that we got there. That is, that we followed in the pen and paper method, which is a triangle ABCD. And 1 minute, I'll show that. So 1 to 2, 2 to 3, 3 to 4, and 4 to 1. This is the graph we saw, right? So for this, what will be my adjacency matrix? My adjacency matrix will be 0, 1, 0, 1, comma 1, 0, 1, 0, right? This matrix is nothing but, this is for A. For 1, it doesn't have path to itself, so it is 0. It has path to second, it has path to second vertex, so 1. It doesn't have path to third vertex, so 0. It has path to 4, so it is 1. 0, 1, 0, 1. I wrote it as 0, 1, 0, 1. For B, it is 1, 0, 1, 0. For B, it has path to 1. 1. For itself, it doesn't have a path. For third vertex, it has a path, so 1. For fourth vertex, it doesn't have a path, so it is 0. 1, 0, 1, 0. Now, what will be for the third vertex? It doesn't have path to this, right? 0, 1, 0, 1. And what will be the for fourth vertex? 1, 0, 1, 0. It is same, right? So I'm simply copying it. Putting in the form. Now I have a graph, and let me take colors. My colors is three. I have three colors RGB. Initially, I'll color all the vertices as in the same color. I'll color all the vertices as 0. I'll mention it as 0. I'll change them afterwards, but this will be my answer. To check them with the condition, I need it. So I may have the solution or I may not have the solution, right? If I don't have the solution, it will simply return as false. So I'll call the graph coloring function here with I'll send the graph and I'll say colors colors. I'll also send this list. That is my answer. I'll send 0. I'll start with 0 and I'm calling this function. After calling this function, if I print color, I should get my solution. Here also I'm giving you the same assignment where it is not possible to color every time with the given colors, right? If I have 5 vertices and I have only 2 colors, it is impossible to form graph coloring, to make graph coloring. In that case, uh, this code will print some random wrong answer, but you have to check it and you have to make the program print. I'll give you the program after completing this. You have to make the program print. The solution is not, uh, we cannot have a solution for this. Solution does not exist. Yeah, it has to print that solution does not exist. Okay. Okay. Now I'm calling graph colors, color, and 0. Right? I have 4 parameters. Graph, color, I cannot type color every time. I'll take M here, color, because colors and color, it will be confusing. So I change it to M. M here is nothing but my colors, number of colors. The 3 in this case. If my V is equals to length of the given graph, that means all the vertices of the graph are colored, right? See, my graph is a 4 cross 4 grid. What will be the length of graph? The length of graph will be 4. That means I have 4 vertices. If V is equal to 4, that means all the vertices, all the 4 vertices are colored. Then there is no need to run the program, right? It's the same condition. If you see here, even there, we we saw that we are incrementing row, and whenever it is equal to the length of board, we return true. We are ending the program. Here also we are doing the same thing. Now for C in range, 1 to m plus 1, I'm checking whether I have to see the condition. If is safe, I'm calling is safe function. Is safe of we don't, okay, since it is in the graph class, we have to, it should be a graph property, right? Graph dot is safe, and what can be my parameters? I have to send it a graph and a color and my color matrix so that it can update it and see. So can I color V vertices with C in the particular, in the given particular graph? If it is possible, then I'm going to color my V vertex with C color if it is possible. Otherwise, if graph of, I have to use recursion. I'm recursively calling the same function which uses the next color. Here we were using the next queen. We are placing the next queen. Here we'll use the next color. And it will return true. And if it is not possible, we have to color of we have to change the color of V to 0. If solution is not possible, we have to go back, right? And it will return false if it doesn't have a solution. Now I have to write isSafe function which will take graph, V, color and C, right? Now I'm going to uncomment this, and the parameters will be graph, V, color and C. We'll give the same parameters. Now we have four parameters. For I in range of, here it will be length of the graph. Length of the graph. Now here I have to keep the condition. What is the condition? My graphs V vertices I is equal to 1 and color of I is equal to C. Then I have to return false, otherwise it will return true. Indentation block. Okay. Be careful of the spelling mistakes. Graph coloring is not defined. It is the same function, right? What happened? GRAPH. Okay. I cannot directly call this function because this is in the class graph, right? So it should be a graph object. I think this will solve our error. Yeah, it is saying 1 2 1 2. So it is saying that this can have one here represents, actually these are ABCDs. We used numbering for colors and numbering for vertices also, so that's why it's confusing. Sorry. So this is my ABCD graph. It is saying this 1 2 1 2, which means where one is, see here, where one is red, two is green, 3 is blue. It's red, green, blue. If we have red, green, blue, we can have the we can color this graph red, green, red, green, so that no two adjacent vertices are of same color. Now we'll try for a different matrix whether it is coloring it correctly or not. Actually, we didn't do any matrix, right? Actually, initially we did, right? So we will see that. I'll take A, B, C, D, E. I'll take E also here, and I'll take. I'll have way to A to B and A to B, and first I'll solve it in paper. Then only we can see whether our program is working correctly or not. So A, B, C, D, E. A to E also I have a solution. I have a path. So A to E and B to C and B to E also I have a path, and C to D. C to D I have a path. C to E also I have a path, and D to A I have a path, and D to E I don't have a path. D to E also I have a path. Let me see. So that's it. A to D I don't have a path. A to D, and I don't have path from A to D. Yeah, this is my matrix. So what can be? I'm giving three colors: red, green, and blue. So one of the solution can be green, red, blue. Green, red, blue. Green, red, blue. Right? Initially we did this. Or give me 1 minute. I'll show you the picture. It's loading. Give me 1 minute. So if you can see here, this is my graph that I drew here. It is the same graph. And when we solved it, we got the solution as green, red, blue. Now let's see with the program that we have. We have to write the adjacency matrix. We have 5 nodes, right? So we'll have 5 cross 5 grid, and we have to see A to B we have. So it is 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1. For B, it is 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, and 1. What for C? For C, it is 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, and 1. What it is for D? For D, it is 0, 0, 1. 0 1 0 0 1 0 0 0 1 0 1 0 0 1 0 1. I'll have one more for E. What it is for E? 1 1 1 1 0. All ones, and we have 1 0. Right? My colors are same. When I'm running, I'm getting 1 2 1 2 3, which is 1 2. If green is 1, 1 2 1 2 3. So we got the solution. Right? So I'll send you this file also. So, for practicing or for revision, whenever you are revising this, find whether you can, whenever there are no optimal solutions, try to print it as there is no solution. Solution does not exist. Try to print that solution does not exist. And give me 5 minutes. I want to show you some a small video, and I'll end it. Here you see, for the Enquin's algorithm, if you use brute force for a 4 cross 4 grid, there will be 320 ways. Out of if you use backtracking, it is reduced by 60. It may not seem like we are doing we are reducing so much time, but if you see, for 4 cross 4 grid from 320 it went to 60 if you use backtracking. This is the importance of backtracking, or the uh, tree space tree, which is very important. The state space tree, if we use state space tree and we try to place them, we will be solving it in 60 ways. For a 6 cross 6 grid, see the drastic change. If you use brute force, it is around 56,000. But if you use backtracking, it is 894. Even if you automate the backtracking, it is less than that. You are not doing it manually, right? And what it is for 8 cross 8 grid, it is 1 lakh. Sorry, it is 19 lakh. No, it is not even 19 lakh. 1 crore 91 lakh 73,000. But if you use backtracking, it is 15,000. So it may not seem like an improvement when you see the numbers, but if you calculate the if you play with the mathematics, you'll change the difference between them. There is one website. I think I have sent you the code, right? Okay. I'll also send you this. This is also for the NQueen's program, NQueen's problem. This is a 4 cross 4 grid. So here, keep an eye on this board. Every time it will use, it is like trial and error method, but it's not trial and error method. Backtracking is a little bit different from trial and error. Whenever it finds a bounding condition, it will stop going further. But in trial and error method, we will see all the problem totally till the end. Then we will see whether it is correct or not. But here it will see the bounding conditions every time. It will check, and then only it will say. I'll just play it. Uh, I'll also send you the link. See how it is placing the queens. It is placing the queen here, the first queen. It is placing the second queen here, but it is in the same diagonal. So I kept it here. It is keeping the same queen, and it is not feasible, so it changed. Now there is no place for the fourth queen, so it will backtrack again, and it will change the position of the first queen to 1 comma 0. It will keep it here, right? Now it is checking every time. It cannot keep the queen here, but it can keep the queen here. It kept the queen there. It can keep the queen there. It kept there. It cannot keep, it cannot keep, it can keep the queen there. So this is one solution. So 1302 is one solution. Here they are, we calculated using the rows, he calculated using the columns. That's it. We got the mirror image, right? 0, 1, 2, 3 is one solution, 1302 is one another solution. Right? So go through this when you are free, and we'll have one more lab 10. Uh, since tomorrow is Ugadi, I think we'll don't have sessions. I don't know. If we have, we'll meet again. Otherwise, we'll meet the day after tomorrow. That is Wednesday. Till then, if you have any doubts, you can ask me, or you can uh, write a mail to me. Okay. Advance happy Ugadi. And yeah, if you don't have any doubts, we can end the session. Okay, guys, enjoy the festival.